Hi everybody, and welcome to a video that is going to work through some of the details that you've already learned about orbitals and hybrid orbitals and how all of this connects to the idea of molecular geometry. So only watch this video if you think you need a little bit more of a brush up on the explanations for orbitals and hybrids in geometry. If not, you can probably skip this video and you should be okay. Ultimately, what we need to be comfortable with is identifying the hybridization of particular atoms within a molecule and then the implications for the geometry based on the hybridization. So if you feel pretty good about hybrid and identifying hybrid orbitals and the geometries associated, then you could probably skip the video. So here we're starting with the basics of atomic orbitals. As you've learned before, orbitals really describe where electrons can be found surrounding an atom, and eventually, as we talk about molecular orbitals, where the electrons can be found in molecules. And we're showing here the good old s orbital and then the three different p orbitals, the px, the py, and the pz. And as you'll recall, and as we'll see again in a couple of moments here, we can combine these orbitals to make hybrids, because ultimately we need to be able to explain the geometries of the particular types of molecules that we'll be looking at throughout the course of not only just this video, but of course the rest of the year. So using atomic orbitals as our jumping off point, let's start to get into some more of the details. Let's not forget, this is all about electrons, and so we have to know where the electrons are. And this is that building up process that you learned back in freshman and in sophomore years. So we have our orbitals. We start with, of course, the 1s orbital, then we have the 2s orbitals, then we have the 2p orbitals, and things can build up from there. But we're just going to look at the first few elements in the main group to see how the electrons build up. And as you'll recall, you always start building at, of course, the lowest energy level. So for example, let's take a closer look at lithium. So we're putting the first couple of electrons here at the 1s level. And if you look closely there, those two electrons are paired, right? One has a spin value of plus 1/2. The other one has a spin value of negative 1/2. And you pair the electrons first. And then once you have filled an orbital, in other words, put two paired electrons at one energy level, one orbital energy level, then you jump up and start filling in the subsequent higher levels. And when you get to the p orbitals, for example, looking at carbon, we fill the 1s, then the 2s, each with two electrons, and then we start filling in one by one the 2p level. And of course, we fill in each individual orbital first, and then only when we have half-filled orbitals, like over here in oxygen, do we begin to pair the electrons again. All right, so this is the electron configuration stuff that we briefly reviewed in class, and you should be able to recall from previous chemistry classes of marching through 1s2, 2s2, and then in this case for oxygen, 2p4, and two of them are paired up and the other two are in their own orbitals, be they the px, the py, or the pz. All right, let's move forward and remind ourselves how now orbitals will help explain how molecules are constructed and how we get bonds out of them. Remember, orbitals are mathematical constructs, so if we look at the simplest molecule one can imagine, hydrogen, H2, we can start with the atomic orbitals 1s and 1s on two different hydrogen atoms. And then because these are mathematical constructs and we do things like linear combinations of these orbitals, don't worry about the math, we essentially get two results. If you start with two atomic orbitals, you're going to get two molecular orbitals. As the second bullet point here reminds us, you always end up with the same number of molecular orbitals as you start with atomic orbitals. So I'm starting with two different 1s orbitals, and I end up with an H2 bonding molecular orbital and an H2 antibonding molecular orbital. And this is where we're going to begin to remind ourselves this orbital here is going to be a sigma orbital, and this turns out to be the sigma star orbital. Okay, keep the idea of sigma in mind as we keep going through this short video. All right, moving on. We then have hybridizations where we can combine the atomic orbitals to get hybrid molecular orbitals, or really hybrid atomic orbitals that then can be overlapped to form the molecular orbitals. Again, it's important to keep in mind that orbitals are a mathematical construct. They are a theory that just so happens to match the observations we can make about atomic structure, molecular structure regarding geometry. So it's really helpful that these things sort of give us the right answer over time. So we have here the carbon atom, and what we're showing is one of the sp3 orbitals that we're eventually going to get through a hybridization process. How do we do this hybridization process? Well, we start with our electron configuration for carbon, 1s2, 2s2, 2p2, and again, the two electrons are in their own p orbitals, say the px and the py. Doesn't matter which particular ones we're talking about. Now, to get the hybridization process going, this particular approach, the approach our textbook takes, actually has us do an excitation of one of the electrons in the 2s energy level and promotes it up to the 2p level to get 3 electrons all at the 2p level and 1 electron at the 2s level. Frankly, this is not really that big of a detail. If I were to have shown this to you in a different way, I think I probably would have shown you all the different orbital levels for carbon without the electrons, and then done the hybridization, and then show you how we can fill in the electrons afterwards. And that's what's being shown here. Don't worry, don't get caught up in the fact that the electrons have all been separated into their own orbitals. What matters is that the hybridization process is going to take everything at the 2 level, at the n equals 2 level, the 2s orbital and the 3 2p orbitals. And again, we're going to do this linear combination process, this mathematical addition of these 4 different orbitals. And what we end up getting are 4 now unique orbitals that are classified as sp3. And of course, the label here is just describing how many of each type of orbital is put into the process to get the hybrid. It's important to notice that the energy level here, the energies are shown on the left, and the hybrids are, of course, a weighted average of the original 2s and original 2p orbitals. So we are kind of, in a way, 3/4 of the way closer to the original 2p energy level with our 4 sp3 orbitals. And then you just go ahead and fill in the electrons based on how many you have for carbon here. We're going to have 6 valence electrons. We didn't do anything to the 2 at the 1s level, and then we fill in 1 each into the sp3 orbitals. Again, we want to put electrons into their own orbitals before we start pairing them for energy considerations, right? That works out nicer because to pair electrons, right, to pair electrons actually costs us a little bit of energy because of electron repulsion. All right, so now we have our sp3 hybrids, and they look kind of like asymmetric p orbitals in a way, where one side is a little bit more, is a little bit larger than the other side. And we can then take these sp3 orbitals and show how we get the molecular structure on the next slide. So here we have for methane, the standard example of a molecule that contains 4 sp3 hybrids on carbon. And in the center here, we have our 4 different sp3 orbitals on carbon, each with 1 electron, as you can see there in white. And then these hybrids are going to overlap with the 1s orbital on each hydrogen, shown for each hydrogen. They'll overlap there, and that's how we get the molecular orbital diagram, the bonding that we observe for methane. And as we know, the hydrogen-carbon-hydrogen bond angle for a tetrahedron is 109.5 degrees. So this is great. Hybridization gives us the right answer. We know that we need a tetrahedron, and when you hybridize an S with the px, py, and the pz, you get sp3 orbitals that give you the required tetrahedral geometry. Let's talk about a molecule that has a little bit more complicated orbital overlap construction, good old C2H4. This is ethene, or sometimes referred to as ethylene. So we have 2 carbons and 4 hydrogens. So ethylene, you can see right here, it's right C2H4. It has a double bond and it's a planar molecule. Each of these carbons is going to be trigonal planar. So how do we get the trigonal planar geometry and the double bond? Well, you've seen this before. What we do is we take one S and 2 P's to get, as shown here in gray, we get 3 different sp2 orbitals, which means we didn't use the third p orbital on each carbon, as shown here in the red and the blue. This is the unused p orbital that didn't get involved in the hybridization. So we can overlap the sp2 orbitals on each carbon that are pointing right at each other to make the sigma bond, as you see right there. We can make the sigma bond. And then we get the pi bond by overlap, of course, of the unused p orbitals that are on both carbons. Right? We get that pi bond going between the 2 p orbitals. So that explains then how we get the 2 bonds between the carbons of C2H4. All right, so let's start talking about geometry. So we know that sp3s produce tetrahedrons. We know that sp2s can produce trigonal planar molecules. So it's important to keep track of what the electrons are looking like in their 3D geometry and what the atoms that make up the molecule look like. So we're going to have an arrangement of the electrons and an arrangement of the atoms. Usually when we talk about the geometry of a molecule, it's this geometry here, the arrangement of the atoms, that we're making reference to. We want to know what the molecule looks like, not necessarily the specific arrangement of the electrons. So here we have a case where we're looking at the different geometries involved in sp3 hybrid structures. Be it methane, ammonia, or water, the central atom, oxygen, nitrogen, and carbon, in these 3 cases, are all going to be consisting of sp3 hybrids. Now this chart is showing you a number called the steric number. This is the same as the idea as occupied areas, the terminology you would have heard in previous chemistry classes. Occupied areas are essentially a bond to another atom or a lone pair on that central atom. So all of these molecules have 4 occupied areas or a steric number of 4. But of course, in some cases we have atoms in those areas, and in some cases we have lone pairs. In the case of methane, of course, we have 4 hydrogen atoms in our 4 areas. In the case of ammonia, we have 3 hydrogen atoms and a lone pair. And in the case of water, we have 2 atoms of hydrogen and 2 areas that are occupied with lone pairs. But all of them are based on sp3 tetrahedral electron arrangements. But then when you look at the atoms that construct the molecule and talk about the geometry that we're really going to care about, well, methane, of course, has the tetrahedral structure. Ammonia has the trigonal pyramid structure with slightly closer angles on the H and H angle because of the lone pair. It causes a minor collapse of that angle between the different atoms. And then water will have its bent structure with an even tighter angle between the atoms because of the 2 sets of lone pairs causing even further collapse of that angle. So to summarize the different geometries that can be produced, let's take a look at this chart. So we already went through the details for sp3. So you've got 4 occupied areas, i.e., in other words, a steric number of 4. So sp3, you're going to have a tetrahedral arrangement of the electrons. And then depending upon the number of lone pairs, you're either going to have none to get a tetrahedral geometry, 1 to get a trigonal planar, or 2 to get bent. How about other hybridizations? If the atom you're interested in, the atom that's going to be in the center and dictate the focus of the geometry, let's say we have 3 occupied areas, a steric number of 3. That's sp2. Now the electrons are going to be trigonal planar. That's going to get the electrons as far away from each other as possible, dictated by the valence shell electron pair repulsion ideas you've learned in the past. Now, if we don't have any lone pairs, then that's how we get our trigonal planar geometry. And we saw that in the ethylene case, C2H4 before. Each carbon was trigonal planar. But if you have one lone pair sitting in place of an atom, then you're going to get another bent type structure for the sp2 hybrid. And lastly, if we have 2 occupied areas, a steric number of 2, we have sp hybrids, and so we know the electron geometry is going to be linear. And at this point, there is no difference between the electronic geometry and the atomic geometry, because even if you did have lone pairs, the electrons are still going to be 180 degrees away from the other side of the occupied area. So we're going to get a linear geometry either way. So whether these gray spheres here represent other atoms, or imagine somehow you have a lone pair where I'm pointing now, you still have 180 degrees. The electrons can't get any further from each other than what they're showing there in the linear structure. So if you feel comfortable pointing at the atom in a particular molecule and identifying the different type of hybridization, and then looking at the molecule as a whole and being able to come up with these different most common types of geometries that we'll typically see in the course, then you're good to go. All right, we'll also make sure that we have some practice sheets associated with this material that we're reviewing on orbitals, but otherwise that's what we're talking about. Hope that helps if you needed a little bit more help, and that should end this video.